Hello. Am I clearly audible?
Yes, sir.
Yes, sir.
Then we can start our today's lecture. So in our last class, we have started discussion on clustering, specifically big data clustering algorithms. And we have discussed one of the big data clustering algorithms. The name of that algorithm is BFR. We have discussed the theories of that BFR algorithm. Okay, I think you have gone through this lecture, and I think you understand the theory behind the BFR. As I already mentioned in our last class, that is maybe many of you have confusion because some theories are some form of abstractness are there, and therefore it's better if we can discuss this one with an example. And therefore I have prepared one example, but I think still we can go through that. We can go through that, and if you have any confusion, then you can ask me again. Okay, before going to discuss the example, I need to remind you that we have also discussed the K-means clustering algorithm in our last lecture, the basic K-means, and I already mentioned that the basic clustering algorithms, those are also necessary to understand our big data clustering, and we have discussed this example. Okay, this example, the basic clustering example, and I want to extend this example, the same example, for our big data clustering. That means in this case we can see that we have this just the 7 individual, and that is all in our data set, and that means that this is the whole data set we consider. And then we can think that we have, maybe we want just 2 clusters, and that's why the value of we assume that value of k is 2, and then we follow just the basic k-means clustering algorithm. I don't want to review this part because we have already discussed this one in our previous lecture. So I assume that you understand this part also. Okay, this part also, and we can see that finally from this data set, we got these 2 clusters, and I assume that okay, you understand up to this one. Now I want to discuss the steps of BFR algorithm. Okay, BFR algorithm. Firstly, we can see that suppose number of clusters is k and number of dimension is d. So the number of clusters is k. That means suppose by anyhow we can know that that is how many clusters will be optimal. In our last lecture, we also discussed about that. That is the how the elbow method is used to find out the optimal value of k. So that's why today I don't want to discuss also that one. Okay, that is I assume that we know how to determine the number of optimal clusters also. And here's the assumption is the number of dimensions. That means in our data set, the dimension is d-dimensional data set. So we are working on a d-dimensional data set. So the first step is load the data points from one file. Okay, that means we can say that okay, we have uh, the big data, and we cannot load the whole data at a time to our main memory. So that's why we want to divide the full data into several files or several chunks, and we can maybe uh, load just a chunk of the data in your main memory. Okay, so here is this, that is load the data points from one file. One file means from one chunk. And then it is mentioned that run k means on a small random sample of data points to initialize k centroids using the Euclidean distance as a similarity measurement metric. So here, that means on a small random sample of data points, that means we have loaded the file or a chunk, but not all the data points are using here in K-means algorithm. We just pick a random sample of data points and try to find out that is the K centroids using the Euclidean distance, and we will apply the K-means algorithm over there. And then, okay, what we will get? If we use the K-means, the result from the B, that means from this step B, to generate a DS clusters. In our last lecture, we know that uh, we have to have that in BFR algorithm we have to form three set of clusters. Okay, one is called the DS is called discard set. Okay, so discard set. So that means use the K-means result from the B, this from this B, from this one, to generate the DS clusters. That means we will get the discard set clusters. And for each and every discard set, we have to have some of the statistics. That means we have to store the statistics for that. And in our previous lecture, we have also discussed about that. That is, what are the statistics we need to store in DS. That is the number of points, then the vector sum, whose ith component is the summation of the coordinates of the points in the ith dimension. And also we have to store another statistic that is called sum of squares. Okay, the sum of the squared sum of the elements. Okay, that is for ith component, the sum of the squared coordinates will be the ith dimensions. So we need to store those things also here in our discharge set. So I can assume that you understand that is what are those statistics and how to calculate that. So now in step 3, we can see use the K-means result from the B to generate DS. So we can generate the DS, that is discard set clusters, and then we will also store the statistics, that is the N, then sum and sum skew. So those statistics we need to store. Then in D, step D, you can see the initialization of DS has finished. So far you have K clusters in DS. That means when we have initialized all these DS, finish the clustering, then we will get K clusters from the random sample of subset of our, that is the fast file or fast chunk. Then after that, run k-means on the rest of the data points. So we have to apply the k-means again on the rest of the data points. That means the data points, those are not clustered in DS. Okay, we have to apply the k-means on rest of the data points. And this time we will assume that the number of clusters will be higher than the k. Okay, for example, the 5 times of k. Though this is the practical case, that in practically we have to assume that the value of k is high on that case, like the 5 times of k. If we consider the k is 2 clusters, then this time we have to think about like the 10 clusters we want to form. Okay, the value of k is high. Uh, to generate the CS, here the CS is our compressed set. In our last lecture, we have discussed about that. That is the compressed set, and we have to uh, we have to form the compressed set. The compressed set is the mini clusters. Okay, that means this time the K-means algorithm, it will form the mini clusters. So in those mini clusters, we will get the number of elements more than one. Okay, but we will get some of the clusters with just only a single point. So those are called the RS. Okay, those are called the RS. RS is a retained set. In our last lecture, we have already mentioned about those kind of sets. That is the discard set, DS, and compressed set, CS, and retained set, RS. Okay, so we have already discussed these three kind of sets. So here we can see that is this time in E step, we need to find out the compressed set, and also the retained set. Okay, we will find out those here. Then after that, what we have to do, load the data points from the next file. Next file, that means we have to uh, load the second chunk of the data, that is next chunk of the data. Okay, we have to load that. Then for the new points, the new point, that means the loaded chunk from the second chunk, from the new point, that is for the new points, compare them to the cluster in DS using the Mahalanobis distance. That means we have to find out the Mahalanobis distance and assign them to nearest DS cluster. Each and every point we need to check. We need to determine the Mahalanobis distance between that point and the cluster, okay, DS cluster. So Mahalanobis distance, it will find out specifically the distance from a point to a distribution. Okay, so here distribution is our DS cluster. We already calculate the centroid of that, and how far the centroid from this data point using the Mahalanobis distance, we can calculate that. There are some actually reason to apply here the Mahalanobis distance instead of just Euclidean distance, because in Mahalanobis distance we can find out the distance from a point to a distribution. Here we assume that is in BFR algorithm, all the data points, all the dimensions are distributed in normal distribution or Gaussian distribution. Each and every dimensional data points are distributed in normal distribution. So that's why instead of directly calculating the Euclidean distance, because in Euclidean distance it will not actually project the distribution, uh, it will just project the distance between 2 points, but it will not consider any distribution. And that's why Mahalanobis distance we have to find out or form. Using the Mahalanobis distance, we have to find out that is how close this points to a definite center of a cluster. And then uh, based on some threshold, like here the threshold is this one, alpha uh, root over d. If the Mahalanobis distance, the value is less than alpha square root of d, here d is the dimension of our data, the dimension of our data. Then alpha you can tune, this is the tuning parameter. Okay, tuning parameter, that means whether you want to keep this one within one standard deviation or maybe two standard deviation or three standard deviation. That's the tuning parameter here, the alpha. And if the distance is less than that, then we can assign that point, the new point, to our DS, that is the discard set. And in discard set, we will not store the data points, but we will store the statistics. Okay, so we will see how it will work in our example. The next is for a new point, that is again we can say the same point. If it is not in, if we cannot place this data point in our DS, then we have to try to place that one in our CS. So that's why for the new points that are not assigned to DS cluster, using the Mahalanobis distance, assign the points to nearest CS cluster. So that means compress this cluster using the same formula. Okay, that is the considering the distance threshold. And again, for the new points that are not assigned to any clusters in DS or CS, then we have to assign those in our RS. Okay, and in our retain set, Okay, so that means we have loaded the data points from the second our second chunk, and then for each and every data point we try to place it in our DS or CS or RS. Okay, based on the distance, that is Mahalanobis distance. And next, mark the data points in RS by running k-means with the. So next, what we have to do, we have to apply again k-means algorithm on our RS set with a large number of clusters. Again, the value of k on that time we have to think about like larger value to generate here CS or RS. So that means now we can say in RS maybe we have many data points, and again what we have to do on those to cluster those data points, we have to apply again k-means algorithm. Okay, k-means algorithm again we have to apply, and then it will form some clusters. So those mini clusters, we will say those are our CS. And if we can find out some of the uh, that is isolated data points, then we will make this one as our RS. Okay, the uh, clusters with just only one point. Okay, RS. Then after that, what we have to do, merge clusters in CS that have the Mahalanobis distance alpha square root of uh, that is D. So we have to try now merge the CS, merge the clusters in CS. Okay, so maybe we will get many CS clusters and then try to merge those clusters. If we can see the Mahalanobis distance between two clusters are very close. Okay, Mahalanobis distance is very close. That means we can say alpha square root of 2. Then we have to merge those clusters. And then repeat these steps f to k until all the files are processed. Okay, so we have to load it again, try to put those new points to DS, try to find out in CS, try to find out the new points uh, to place in RS, and then merge clusters of RS to form the new CS and RS, and then merge class 2 or maybe more CS clusters. Those are uh, very very closer. Okay, that means based on the Mahalanobis distance, we can also merge two CS clusters. You have to do many times, but the last step here, that is if this is the last round, so that means after processing the last chunk of data points. Okay, so that is our last round. Merge clusters in CS with the clusters in DS, and that have the Mahalanobis distance alpha root of D. Okay, so that means the final try, what we have to do, we have to merge the CS, that is the mini clusters, try to merge the mini clusters with our larger clusters, that is the DS clusters, uh, and based on okay, based on the Mahalanobis distance. Finally, we will get the cluster k number of clusters. Okay. Now maybe we can see some of our the steps here in our algorithm, in our example. So let's say the same example specifically I discussed in our last class for the basic k-means clustering. So I have used this data set. Okay, but in this case we can see we have only 7 individual, and we have like the two variables, this variable 1 and variable 2. We want to form two groups of individuals here based on the properties, that is the variable 1 x1 and variable 2 considering these two. Based on these two features, we want to form just two groups. But now consider that we have actually the large data set. We have the large data set, and those data sets are loaded in several files or several chunks. So let's say load the first chunk of the data. Okay, so consider that in chunk 1 we have this information, we have this data. So in this case we can see individual 1 to individual 14, and the two features are x1 and x2. Just we have two dimensions here. So these are the first chunk of the data, here. So according to our algorithm, load the data points from the from file. That means we have to load the first chunk and then run k-means on the small random sample of data points. That means we have to apply k-means algorithm on a sample of random sample of data points from the first chunk. Okay, so that means this is the first chunk. Now we should pick the random sample of data points here from here and then apply the k-means algorithm on their data set to find out the clusters. Okay, so uh, I just pick a random small subset of instances and apply the k-means clustering here. Okay, so in this case, I assume that okay, maybe I just picked from 1 to 7. 1 to 7. Okay, that means this part. I just sampled this part of the data. So here is the I1 to I7. Okay, I1 to I7. And then apply the k-means clustering algorithm. So k-means clustering algorithm, and we know how to apply that. Okay, that means the Euclidean distance we need to measure. Uh, Initially, we have to find out that this is the center of cluster 1, and I assume that this is the center of cluster 2. Okay, and then find out the distance, Euclidean distance. Similarly, I can see the same data point. If we consider reference data point 2, that means the I4 here, this one. Then distance from each and every instance to I4, I have calculated those. And then we can see that is from I1, what's the distance of cluster center 1, and from the I1, what's the distance of cluster center 2. I have calculated those distances here. Actually, this is the same we have calculated in our last lecture here. You can see that is from I1 to I7. I1 to I7. This is the data set, and I have just randomly picked. I consider that okay, I have randomly picked I1 to I7 and then apply k-means clustering algorithm over there. And you can see that is the from I1 to cluster center 1 distance is 0, I1 to cluster center 2 this distance is 7.21. Okay, so here is this. That is from I1 to centroid 1 0 and I1 to centroid 2 7.21. Like this way we have to determine the distances from each and every individual to centroid 1 and centroid 2. Each and every individual to centroid 1 and centroid 2. So in this way, that means we have to apply the k-means clustering algorithm. So I think no need to discuss in details how the k-means clustering clustered those data points. Okay, so I want to just take the output of our k-means clustering here. So we have applied 3 iterations. In our last class, I have already discussed. Okay, and after 3 iterations, we got the clusters. Okay, we can see here in our cluster 1, C1, we have these 2 points, 2 data points, and in cluster 2, we have these 5 data points. Okay, we have the 5 data points. So I think no need to explain in details how to get those data points. We have already discussed in our last class. But we need to continue here. Okay, so that's why continue iterations as we have discussed in our last class. After third iteration, we will get in C1 in cluster 1 the individual 1 and 2, and in C2 we will get 3, 4, 5, 6, and 7. So here we can see individual 1 and 2 in cluster 1, 3, 4, 5, 6, and 7 in cluster 2. So is there any question up to this point? Do you have any question, concern? I think no question. Okay, then next we need to continue. Okay, after third iteration, we will get these two clusters. That means we can say that actually these two clusters, those are in our DS. That is discard set. That is our discard set. So we can consider that is we have two clusters. One is C1 and another one is C2. And here we can see that is the cluster center of C1. It is M1. Cluster center C1 is M1, and the value of the first dimension is 1.25 and second dimension is 1.5. If you can remember here, that is the centroid we have calculated. M1 is 1.25 and 1.5, and M2 it is 3.9 and 5.1. Okay, so that's what it is written for M1, 1.25 and 1.5, and for M2 it is 3.9 and 5.1. Okay, those are the centroid of cluster 1 and cluster 2. And how many elements in cluster 1? We can see we have just 2 elements. And how many elements in cluster 2? It is just 5 elements. Now we can see that is the this is our C1 and this is our C2, cluster 2. And we have to consider those in our DS. That is the cluster 1 and cluster 2 is in our CS. Then we have to store some of the statistics here, some of the statistics in DS. That means we have to find out that is the for the cluster 1, what's the sum of dimension 1. The sum of dimension 1, that means we can see this is our cluster 1. The sum of dimension 1 is, this is the two values we have to sum up, 1.5 and 1, so it is 2.5. And for the C1, that is cluster 1, sum of dimension 2. So this is the dimension 2 we have. The sum is 1 plus 2 is 3. So here is the 3. Then we have to store that is the for the cluster 1. So sum of squared elements. Okay, so we can see um, for the first dimension. So the elements here, those are just one of those elements, that is a square summation. The first element is 1, the square of that, plus second element is 1.5. So you can see here 1 square plus 1.5 square, you will get that is 3.25. You can see here there is 1.5, the square of that, plus 1. Okay, so it is 3.25. Okay, here is the 3.25. Then we have to think about, like, for the dimension 2, sum of squares of those elements. Sum of squares of those elements is 1 square plus 2 square. So it means we have 1 plus 4 equal to 5. Okay, that is 5. Here is the 5. So we have to compute that also. Why you are asking this question at this moment? Mashtura Majid. We can discuss it, I think, at the end of the class, but the middle of the class when I am delivering a lecture on it, you can ask me the question on it. I think it's not the right time to discuss whether there will be midterm. Okay. Okay, so here is the this is the sum of a squared for the dimension 2, the sum of a squared elements of dimension 2. Okay, so those are the statistics we need to hold, we need to store these statistics from the C1. Similarly, from the C2 also we have to store those statistics. So in this case, we can see for the cluster 2, for the sum of dimension 1. So that means we have to just sum up all these values and you will get 19.5. And then for the second dimension, for C2, the second dimension, if we just sum up those values, then we will get this value. Similarly, we have to find out the sum of the squared elements. Okay, so that means so it is 3 square plus 5 square plus 3.5 square. 4.5 square. Then 3.5 square. Uh, for the first dimension of C2, you will get 78.75, and for second dimension you will get 135.25. Okay, so these are the statistics, and now we can see these statistics we need to hold. Okay, we need to hold these statistics. That means we need to store those statistics. And after that, what we have to do after that, okay, so still we can see that we are still in our that is the first chunk, and we have just randomly selected data points of our first chunk, and from there we form two clusters, that is C1 and C2, and we hold the statistics of those two clusters, that is C1 and C2 clusters. Now what we have to do, we have to determine that is the standard deviation of our the elements of cluster 1. That is called the C1 sigma of first dimension and C1 sigma of second dimension. Similarly, the C2 sigma of first dimension and C2 sigma of second dimension. It means we have in cluster 1, C1, we have these elements. What's the standard deviation of these elements of its first dimension? So that is our C1 sigma of first dimension, and C1 sigma of the second dimension, that is what's the variability or what's the standard deviation of the elements of the second dimension of first clusters. Okay, so we will determine that and you will get this. So how to calculate this one, how to calculate this this sigma? I think in our last class I have already shown that. So the variance and standard deviation, the standard deviation we will get is the square root of that. So this is square root of this value. Okay, square root of this value. So we can see sum of SQI, that means sum of squared elements divided by n minus of sum of the elements divided by n whole square. Okay, so using this formula, using this is a very well known formula for finding out the variance and the standard deviation. So we can utilize this formula to find out the standard deviation, that is the sigma there. Okay, sigma there. So in this case we can see here to find out this value. So what we need actually, so this is for the first dimension. Okay, for the first dimension, uh, what we have to do, we have to calculate the square root of, this is the cluster 1, the cluster 1, then the squared sum. Okay, sum of squared elements, sum of squared elements of first dimension, it is 3.25, 3.25, and divided by n. N is the number of elements in this cluster, so n is 2. For the cluster 1 it is 2, and then minus, then sum of those elements. So sum of those elements, we can see for the first dimension the summation is 2.5. So here is the 2.5 divided by the number of elements, that is the n. N is 2, the square of that. So this is our C1 sigma 1. Okay, so we can find out this one. So we can see that these statistics actually help us to determine this standard deviation. Okay, similarly, to find out the that is the standard deviation for the dimension, the second dimension, this dimension, we will apply these statistics. Okay, these statistics, that means for the second dimension, sum of squared values, those are 5, divided by number of elements is 2, and minus uh, then sum is what? Sum is 3 by 2 whole square, and square root of that, then we will get this value 0.5. Similarly, we have to find out the C2 sigma 1, that is standard deviation of the elements of first dimension of cluster 2, the standard deviation of the elements of second dimension of cluster 2. So we will get those values using just only these statistics. So no need to store those values, but we need to store those statistics to get these values. Okay, to get these values. And now you can see here that is what we have to do next. So we already got the DS, and we store the statistics of the DS, and we have the standard deviation with respect to first dimension and with respect to second dimension of cluster 1 and cluster 2. Okay, so those are the necessary things. Now, according to our algorithm, so here load data points, run k-means algorithm, and use k-means to generate B. Here the DS clusters, we got the DS cluster. The initialization DS has finished. So far you have k clusters in DS. We already got the 2 clusters in DS. So now this is the point we have to apply. So that means this is the point now. So run k-means on the rest of the data points with a large number of clusters, 5, to generate the CS and RS. Okay. So rest of the data points, it means from the first chunk of our loaded data points, we have taken some of the random instances. Then except the random instances, the rest of the data points are mentioned here. Okay, the rest of the data points, except the there is the small random samples we have taken, the rest of the data points here. It means in the rest of the data points, we have to apply the k-means algorithm again. So now if we go back to our example, so in this case, we can see that is, we have in our original data set, we have those values, but first part, that means the first I1 to I7, we have applied already k-means algorithm, and we got 2 clusters in DS. and the rest of the data points are from I8 to I14. So these are our rest of the data points. So that's what we have taken the rest of the data points here. So these are our rest of the data points. So it is mentioned that take the remaining data of the fastly loaded data chunk. Okay, so these are the rest of the data points. Now what we have to do from the rest of the rest of the data points, for each and every data point, like maybe if we consider I8, if we consider the I8, uh, then I8 here, in this case, we can see there is I8. In I8, we have two variables. These are the variable values, 1.5 and 2. So from this data point, if we consider this is our a data point, that is the P, we have to find out the distance from P to our, there is the cluster center, okay, cluster center of cluster 1, cluster center of cluster 1, and also the cluster center of cluster 2. Then how can we find out the distance? This is called the Mahalanobis distance. We have to find out the Mahalanobis distance from each and every data point to our distribution. Here distribution is the cluster, okay, cluster center. And in our last class, I have also discussed about our Mahalanobis distance formula. So this is the Mahalanobis distance. If we consider a data point, so this is the data point, this is our P. And then a centroid, that is a cluster center, that is, if we consider C1 cluster center, it has the dimensions also, okay? That is, for each and every centroid, usually we have the dimensions. And for each point, usually we have the dimensions. Now we want to find out the distance from P to C1, P to C1. And for that, what we have to do, normalize in each dimensions by using this formula. So here we can see xi minus of ci, and then we have to divide it by sigma I. Then we will get yi, okay, yi. Then take the sum of squared of the yi. We have to take the sum of squares of the yi. So we can see this part actually is here. Okay, this part. And then square that. So that means this is the second step, that is square it. And then take the square root of, that is, take the sum of squared. So sum of here the summation, here the summation of the squared values of normalized dimensions, and then take the square root of that. So this is the square root. Okay, then we will get the distance, that is Mahalanobis distance, from the x, that is from the P to the C. Okay, so here is the C. So we will get this distance, Mahalanobis distance. So here we can see we want to find out the Mahalanobis distance. Now we want to find out the Mahalanobis distance. Okay, then how to find out the Mahalanobis distance? So in this case, we can see the P, the data point, we have the P, that is the data point here, x1 and x2. So for the I8, it is x1 is 1.5 and x2 is just 2. Okay, and consider our that is the cluster 1. Cluster 1, what's the value of a centroid? The centroid, The cluster 1 centroid, the value of the cluster centroid already we have here. There is 1.2, 1.25 and 1.5. So it is 1.5 and 1.25 and 1.5. 1.25 and 1.5. Okay. We can determine also these values specifically using these statistics. Okay. Using these statistics. Okay. So here we have already known that these are the cluster center. Okay. Cluster center for cluster 1. But how to find out the Mahalanobis distance? Specifically, if we want to find out the y, okay, then here it is like x I and ci. Okay, so xi is what? 1.5. This is our xi, and then the ci. So here is this one minus of 1.25 divided by sigma I. Okay, that is first dimension. So we have the first dimension sigma I of first dimension is what? This is the sigma for the cluster 1. So it is 0.25, 0.25. So this one, and then take the square. Okay, so that means we can see here xi minus ci. So xi, the value of first dimension, minus ci, the value of the center of the first dimension, minus sigma I. That is the standard deviation of the first dimension. Okay, then we will get y, and then we have to take the sum of squares of the yi. So we have to square the term. We have to square the term. That means this one we have to square it. This one, okay, and then that is we have to take the summation of the summation over dimensions. We can see summations, the summation over the dimensions. Okay, I equal 1 to 2. So we have considered the first dimension, then we have to consider the second dimension now. So that means we can see that for the second dimension it will be 2 minus 1.5. For the second dimension, what will be the sigma? And we can see sigma in second dimension 0.5. Then take the square of that, and then we will get what? We will get that is sum of squared values. Okay, so we will get this part. Then what we have to do? We have to take the square root of that value. So square root of that value. So that means the square root of these values to get the distance. So distance from where to where? Distance from I8, the data point, or I8 to C1. C1, that is a cluster 1. We will get this distance. Okay, this will be the distance, and this is the distance here. You will get 1.4142 like this. Then similarly, what we have to do, we have to find out the distance from here, that is I8 also, to our cluster 2. Okay, that means it will be the same, or P or I8 1.5 and 2, and our C2, we know the C2 here. The C2 is this one. Okay, that is centroid of our cluster 2, 3.9 and 5.1, 3.9 and 5.2. Okay, so we want to find out the Mahalanobis distance between these two. Then it will be at first we need to find out the actually this is a standardization. We have to standardize this. So for a standardize, it is 1.5 minus 3.9 divided by sigma. So for the cluster 2, what's the sigma? For the cluster 2, the sigma of first dimension 0.7348. So we can say 0.735, 0.735, 0.735. Okay, then a square plus of, for the second dimension we will get, again here is the 2 minus 5.2 divided by what? Divided by, for the second dimension, what's the standard deviation? It is 1.02. Okay, 1.02. Let's say it is 1.02 square of that. And then we have to take, that is, if we want to find out the distance from I8 to our C2, then it will be the square root of these two values. Okay, so then we will get the D. This is how we can calculate this distance. Okay, this distance. Similarly, for each and every data point, those are just remaining data points, that is I9, we have to calculate the distance from the data point to C1 and distance from the data point to C2. Okay, similarly for I10, I11, I12, I13 and I14 up to that. So you have to find out the Mahalanobis distance. Okay, so after determining the Mahalanobis distance, what we have to do, the next thing is uh, some of the data points, it will be added to our DS. Okay, so it will be added to our DS, and some of the data points it will be in our CS, and some of the data points will be in our RS. Okay, so considering here the MD threshold, that is our Mahalanobis distance threshold, uh, that is square root of D. So square root of D, it means in our case we have two dimension. So two dimension, that means root over just 2. So root 2. So root 2, it is 1.414. Okay, considering alpha just 1, alpha equal 1. So that means we want to pick just within the one standard deviation, those cluster, kind of compact clusters we want. Okay, considering that, then take the data point I14. So if we consider I14 here, so we have to check each and every, that is I1, I8, I9, I10. So we can think about like I14, just maybe in bottom-up approach. So think about I14 here. In this case, we can say distance from this from I14 to C1 is 11 point something 40, and distance from I14 to C2, it is 0.553. So which one is minimum? The minimum is this one. Okay, this one is minimum. Then whether this minimum one holds the condition of our Mahalanobis distance threshold or not. So this one is actually less than our Mahalanobis distance threshold, that is 1.414. This value is less than that. So if this value is less than that, then we have to add this one in our DS, in our that is discard set. So that's what we have done here. Take the data point I14, the I14 to C2, it is less than, so that means update the ds to c2. Okay, c2, that means c2, we have to update the c2. Previously we can see in our c2, this is the statistics we have in our c2. c2n, that is number of elements in c2, is 5, and the sum is this one, and sum of dimension 2 is this one, and sum of squared elements of dimension 1 is 78 point something. Sum of squared elements of 2 is this one. Okay, so we can see that we have to add this one I14 in C2, because we can see the distance from C2 to I4 is minimum, and that is also that holds the minimum threshold criteria of our Mahalanobis distance. So that's why we have to add this one in our C2. So we can see here C2. Now if we add this I14, in C2, the number of elements, it will increase to 6. Previously it was 5. It was 5. Now number of elements is 6, and we have to add the value also. That is the for the I14, we can see for the I14, the x is 3.5 and x2 is 5. Okay, so we have to sum in first dimension, that is 3.5. So previously C2 sum, it is 19.5. So 19.5 plus of 3.5. 3.5. So it is 23. There is 23. And we can see here it is 23. Similarly, we have to add the sum also in second dimension. So 5 added in second dimension. So second dimension is 25.5 plus of, you have to add this, that is the 5. So it is 25 25 and 5, it is 30.5. So it will be 30.5. So here is the 30.5. Similarly, we have to update also the sum of squared elements for the first dimension and for the second dimension also. That means we can see in this case you will get the sum of squared value, this one, then plus of sum of squared, that is this one plus 3.5 whole square, 3.5 whole square. And if we do the math, then you will get 91. And for the next one also, sum of squared of our second dimension is 135 plus 135.25 plus of 25. There is a 5 square. Okay, so we will get this value, 160.25. Okay, so that means we have to update the statistics of C2. So if we update the statistics of C2, what will happen? The same time, the sigma of C2 will be updated. Sigma 1, sigma of dimension 1, that is the standard deviation of the first dimension of cluster 2, standard deviation of second dimension of cluster 2, and then the mean of the first dimension of cluster 2 and mean of the second dimension of the cluster 2, it will be updated. Okay, it will be updated. And we can see that specifically in our cluster, the new elements will be added. So in our previously we have in cluster 1 and 2 just 2 elements, but in next cluster C2, that is the new element here is 14. Okay, I14. So this one is the new element is added to cluster 2, not in cluster 1 but in cluster 2. Okay, similarly what we have to do, we have to check again. Okay, um, check again, then we can see that I13, none of the distances is less than 1.414. For I12, none of these two distances less than 1.414. And for I 12, sorry, I11, none of these distances are less than that. Okay, then how about I10? Yes, this distance is less than 1.414. So that means I10 we have to add it also in C2. I10 we have to add it also in C2. So the I10 we have to add it in C2, and we can see that here is the I10. I10 is less than 1.414. So update the DS of C2. Okay. So here now you can see previously it was 6 element, now it is 7 element, and we have to update the corresponding statistics also. And if we update those corresponding statistics, the standard deviation also updated, the mean also updated. Okay, so those values will also update, and we can see in our C2 the new, there is the 10 I10 also added here. So it means that then we have to check, there is I9, we can see here the 13, here is the 1.35. Okay, 1.3528 and 1.41, here is the 1.35. So is it 1.35? That means we have to add this one also. 1.35 is 1.35 is also 1 point less than 1.414. Okay, 414. So that means, am I right? Yeah, 1.35. So this one we have to add it also. That is I9, we have to add it in our C2. But I8, we can see here I8 1.414. So actually this is not less than but equal. But our condition is we have to the MD, Mahalanobis distance, must be less than uh, our 1.414. But this is not actually less than. Okay, so we can say we should not take it. Okay, I think I made a little mistake here. The I9, though here is 1.35, though 1.35, but I have not taken that one in C2. Okay, but we have to take it because the distance is less than 1.414. Okay, so this is just a mistake from my side. Okay, I have not taken that one. Uh, so you have to take it. Please correct it. That is, you have to take the I9 also in C2. Also in C2, you have to add like similar way. Yeah, similar way. That means on that case it will be C2n equal 8. Okay. Uh, Now what else we have? That means except those are incorporated in our C2 or C1, C2 or C1. The rest of the elements in this case, you will get I8, I9, I11, I12, and I13. Okay, so you will get these elements, the rest of the elements. What we have to do, we have to apply again the K-means clustering algorithm here. K-means clustering, and we have to increase the number of the K. Usually, if you can say if you want to implement it, but for the simplicity, I have just considered the same K, that is K value equal to, but uh, practically you need to increase it. Okay, so here considering the K equal to, in my case I have considered just K equal to, and then apply the K-means algorithm here. If we apply the K-means algorithm here in this case, then I think we know how to calculate the K-means clustering values. Okay, so initially I have taken I9 and I13. So here is the I9 as our initial, that is the centroid. Okay, initial centroid I9 and I13 initial centroid, and then find out the distance from I9 to our uh, the cluster center 1 and cluster center 2. Okay, so after that the distance, you will get the distances here. These are the distances. So these are this Euclidean distance. Okay, Euclidean distance. And now based on this, specifically we have to do maybe many iterations. So I have just considered that I get the solution after first iteration. Okay, practically we have to do many iteration to find out that. And after that we can see that uh, in this case, if we compare between these two values, then this is the minimum one. Okay, so I8 we have to place, that means if we can consider that is cluster 1. So this time we have to say that these are our compressed set. This is cluster, the mini cluster, but we have to say those are our compressed set. Compressed set 1 and maybe the compressed set 2, and then okay, now we can see I8 compare between these two values, which one is minimum. Minimum is this one, 60. So that means I8 we have to place in C1, so I8 here. And then for the I9 here the 0 and 1.1, that means I9 also in cluster 1. And then I11 you can see I11 is 2 and 2. So that means I11 also we have to place here, I11. Then I12 uh, if we compare between these two, then this one is minimum, so that means I12 also I have to place here. Okay, I12. And how about I13? I13, this one is minimum, that is C2 is minimum, so I have to place in compressed set 2 the I13, compressed set 2. Now we can see that in compressed set 1 we have 1 2 3 4 elements, and compressed set 2 we have just one element. So if we find something just isolated, instead of compressed set we have to rename it like this is retained set. The retained set is I13, but in compressed set we will get these 4 elements. Okay, so that means the compressed set 1, those 4 elements, that I8 9 11 and 12. Okay, so those elements we will get in compressed set, and in our retained set the I13. So here is the I13. In retained set, what we have to do, we have to just store the whole data point. That means I13, and then the 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 first dimension is 5 and second dimension is 3. Here is the first dimension is 5 and second dimension is 3. So the whole data points we have to store. But for the case of the compressed set also, we have to store only the statistics. The statistics. That means in this compressed set, how many elements are there? Total 4 elements. And then the summation of the first dimension. So that means we can say summation of these values. Then summation of the second dimension, summation of these values. The summation of squared elements. Yes, here is the 1.5 square plus 4.5 square plus 2.5 square plus 4 square. So that is 44.75. And then a squared sum of the second dimension elements. Okay, so a squared sum here is 2 square, 4 square, 4 square plus 7 square equal 85. Okay, so if we know these statistics, then we can also determine the sigma. Okay, the sigma according to the equation we have already discussed, and for sigma for the second dimension, and mu, that is the mean for the first dimension, and mu for the second dimension. Okay, so the compressed set and their statistics we have, and then RS is there. Okay, now actually this is the end of our uh, that is the operation on the loaded chunk of fast time. That is in our load the first chunk of the data. So we have loaded to the memory the first chunk, and then we have done those operations. Okay, up to this. Now what we have to do, we have to load the second chunk of the data. So on the first chunk of the data, we can see that just only we hold the information of or statistics of our DS, the discard set, and then information of the CS, that is our compressed set. And in RS, only in RS we store the data points. But in DS and CS, we store the statistics only. Okay, we store the statistics only. Now load the second chunk of the data. And then we can see that in the second chunk of the data, consider that, okay, in our second chunk, we have I15, 16, 17, 18, 19, 20, and 21. So this is our second chunk of the data. Then again, from each and every data point, we have to find out the Mahalanobis distance. Okay, Mahalanobis distance. And we know how to calculate the Mahalanobis distance. I think no need to discuss it again. Okay, so how to calculate the Mahalanobis distance? Then we have to calculate the Mahalanobis distance from I15, and you will find this value. Mahalanobis distance from I15 to our cluster 2. So this will be the distance here. This will be the distance. Okay. So similarly from I16, I17, I18, I19, I20, I21. So that means in our DS, we have two clusters. That is cluster 1 and cluster 2. And we have determined the distance of each and every individual of secondly loaded data point individual. We have calculated that the distance from cluster 1 and distance from cluster 2, that is Mahalanobis distance we have calculated. So these are the Mahalanobis distances we have calculated. And now again, what we have to do, we have to find out that whether any of these data points we can place in DS. So at first we have to try that. Okay, so we have to try that, and we can see that okay, between these two data point, we can see that there is this value is less than our threshold of Mahalanobis distance, 1.414. So that means this I21 we have to place in our C2 again. So now we can see the C2, the value of C2 is 8. Previously it was 7. Now think about I20. We can say no, we cannot. I19, no, we cannot. I18, yes, we can place. Okay, we can place it. We can see here is the 17 distance, and the distance is 1.40. So 40 is, this one is less than our 1.414. So that means I18 we can add to our C2 also. So here is I18 we have added to C2. Okay, then this is the case. Okay. Now how about I17? Yes, I17 also, because we can see that this is less than 1.414. So we have to add this one also in C2, okay, because the distance is from the I17 to C2 is less. So we have to place, here you can see now 10. And corresponding statistics we need to update. So we have updated the corresponding statistics also. Then next, we have to check the I16. We can see no, we cannot add I16 to our DS. And how about I15? No, we cannot add I15 to our DS. Okay, so that means 3 data points from our newly loaded chunk we can add it to our DS. Now think about our CS. Can we add any data points to CS or not? And for that, again, we have to determine the distance from the rest of the data points to our, that is the CS. Okay, so here we can see the rest of the data points. We have these 4, and our CS, we just have just only one CS. Okay, that is the compressed set. We can see we have just only one CS. If we have 2, then we have to compare both 2. If we have 3, then we have to compare all of these 3. So here we can see only one CS. So we have to use these statistics to determine the Mahalanobis distance. Okay, so here the CS1 to D1 and CS1 to D2, dimension 1 and dimension 2, and we can see that there is D of X of CS1. It is not C1, it is CS1. CS1, the distance from X to CS1, and these are the distances. And now we can see there is again check I20 whether we can add I20 in our CS or not. We cannot, because the 1.53, it is greater than 1.414, that is Mahalanobis distance. I19 cannot, I16 cannot, but yes, we can add this one, that is I15 to our CS. Okay, so that's why we have added. Previously in CS we have 4 elements, only 4 elements, and now we can see we have another one, that is the 5 elements, and update the CS statistics and the corresponding sigma and mu. Okay, now we can see that, okay, the this one, this I15 also added in CS, but the other 3 elements, I16, I19 and I20, we cannot add those elements to our CS. Previously we tried the DS, we cannot, but now we try the CS, and we are not successful to add those 3 elements in CS. So that means these 3 elements, what we have to do, we have to place in our RS. So now we have placed these 3 elements in our RS. Previously we have 1 element in the RS, so just I13 RS. But now we have to add 3 new elements here in RS. Now what we have to do, we have to apply K-means algorithm to on RS. Okay, so here is the RS. We have 4 elements, and we have to apply the K-means algorithm again to find out the clusters here. So okay, so on for that case, again we have to apply the K-means clustering. We know how to do that, and specifically we can see that is the um, uh, I have considered the reference point of cluster 1 is just I13, and another cluster is I20, considering the k equal to, and then we got those distances. Okay, the distances, and now we want to compare the distances here. Distances, okay. So now what I have done here, that is we have CS, just only one CS previously. This is one CS, and the RS, if we cluster those elements and if we get the clusters of more than one element, then we have to say those are also CS, the compressed set. Okay, compressed set. So that's why in this case what I got just here 2 clusters. Okay, 2 clusters here. After continued many iterations, maybe the clusters in C2, CS2 and CS3. CS1 we have already here, the compressed set one. Now I can rename this one as CS2, and we can see between these 2 values 0 is the minimum one, so that means I3 I have to place CS2. We have 2 compressed set, so the name here is CS2 and CS3 because we have the CS1. Okay, so between these 2 0, that means CS2 I13 I have to add in CS2, and between these 2 values one is minimum one, that is I16, I have to place. Okay, and then I19, between these two, which one is minimum? This one is minimum. This is 427. So I have to place this one in I here, I19. And then I20, we can see this is the minimum one. So I have to place I20 in CS3. So it means that CS2 consists of two elements and CS3 also consists of two elements. So that means we have to say those are our CSS. There is no retain set in this case, because in retain set, if we have just only one element in a set, then we will call that one a retain set, but we don't have any retain set. So now we can say CS, we have several CS. Previously we have this one, CS1, and the newly added CSS are just CS2 and CS3. So this is the set of CSS we have and their corresponding statistics we need to store. But we can see that in our RS, there is no element at this moment. The RS is just empty, okay? There is no element at this moment. So I have just stop here. What we have to do, you have to complete this assignment, okay? You have to complete this assignment. What next you have to do? We can see so I have done up to this point in this example. That is mass data point of RS by running k-means with large number of clusters to generate CS and RS. So I have already generated the CS, and in our RS set there is no element, okay? So I have done up to this. Then the next thing you have to do, that is the try to merge cluster of CS that have the Mahalanobis distance less than alpha. So considering the alpha equal 1 and D, our dimension D is the 2, D is the 2. So it is the MD less than 1.414, okay, 414. So what you have to do, you have to apply this operation, merge cluster CS that have the Mahalanobis distance less than this one, okay? So just apply this one and finally apply this one. No need to repeat these steps, okay? No need to repeat these steps. Maybe we are done, just we have maybe two chunks. First chunk we have added, and then the necessary operations we have done, and second chunk we have added, and the necessary operations we are almost done, except these two steps. So this is your assignment, that is you have to just apply these two steps in our example, in this example, okay, in this example, and complete the algorithm. So if you want to apply these two steps, then again, whatever I have done so far in this, if you understand those, then you can apply. So any question from your side? If you don't understand any step here?
স্যার প্রিভিয়াস ক্লাসের রেকর্ডিংটা মনে হয় আপনি আপলোড করেন নাই ক্লাসরুম।
Okay, then I will upload it.
স্যার যেগুলো স্লাইডস আপলোড করা আছে ওইগুলোর মধ্যে আমাদের মানে টিল মিড আর কি কোনগুলো লাগবে একটু বলা যাবে? কারণ লেকচার 3
আসলে
3টা
এখনো মিড নিয়ে আমি চিন্তা করিনি, হ্যাঁ।
আচ্ছা ওকে,
চিন্তা করিনি, এজন্য হচ্ছে আমার মনে হয় যে যতটুকু আমরা হচ্ছে মিড টার্ম আগ পর্যন্ত কভার করতে পারবো সেটাই মিড।
ওকে স্যার।
স্যার আজকের যে স্লাইডটা পড়ালেন এটা কি একটু সেভ করে শেয়ার করা যাবে? একটু করলে ভালো হতো।
সেভ করে, তাই তো? তার মানে
জি স্যার। জি স্যার।
জি স্যার।
ওকে।
আর স্যার আজকের কি ক্লাসের রেকর্ডিং করা হইছে?
হ্যাঁ, রেকর্ডিং আছে।
স্যার লাস্ট ক্লাস এন্ড আজকের ক্লাসের রেকর্ডিংটা একটু যদি শেয়ার করে দিতেন।
ওকে, নো প্রবলেম। I'll
ওকে
share it. Midterm কি সাজেশন? মিডটার্ম ঈদের পরে নেওয়া পসিবল কি না? আমরা নেক্সট ক্লাসে তাহলে মিডটার্ম নিয়ে কথা বলি, হ্যাঁ? মিডটার্ম এত তাড়াতাড়ি চলে আসলে একটু বিপদই হয়ে যায়। ওকে, ঠিক আছে, আমরা মিডটার্ম নেক্সট ক্লাসে কথা বলবো। আমাদের একটা এক্সট্রা ক্লাসও নিতে হবে আর কি। একটা ক্লাস আমরা মিস করছিলাম, যদি তোমাদের মনে থাকে আর কি। ওকে, ঠিক আছে, থ্যাংক ইউ ভেরি মাচ। অ্যাটেন্ডেন্স সবার?
সরি স্যার, অ্যাসাইনমেন্টের প্রবলেমটা একটু বলা যাবে আরেকবার, ঠিক এক্স্যাক্টলি কি করতে হবে?
আচ্ছা, এখানে হচ্ছে আমি জাস্ট এখানকার এক্সাম্পল যেটা, সেই এক্সাম্পলটা বিল্ড আপ করার জন্য আমি লাস্টের দুটা স্টেপ হচ্ছে একটু ব্ল্যাঙ্ক রেখে দিছি। দ্যাট মিনস এই দুটা স্টেপ আমি করি নাই। অ্যাসাইনমেন্ট হচ্ছে এই বাকিগুলো তো করেই দিছি আমি, এটাকে কমপ্লিট করা। তো কমপ্লিট করতে গিয়ে মেইনলি দুইটা স্টেপ করতে বললাম, সেটা হচ্ছে এই আমরা ক্লাস্টার সিএসএ যেগুলো পাইছি অলরেডি মনে হয় কতটা, 3টা ক্লাস্টার সিএসএ আছে। হ্যাঁ, CS1, CS2, CS3 এই 3টা ক্লাস্টার আছে। এই 3টা ক্লাস্টারকে আমরা মার্জ করতে পারি কিনা? তাহলে এখানেও মার্জ করতে পারবো যদি তাদের মাহালানবিস ডিসটেন্স এটা হচ্ছে স্যাটিসফাই করে, তাহলে আমরা মার্জ করব। না হলে ওদেরকে মার্জ করব না, যেরকম আছে সেরকম, বা যে দুইটাকে মার্জ করা যায় সেই দুইটাকে করব, আরেকটাকে রেখে দিব। এটা আচ্ছা। এরপর লাস্ট স্টেজে যেটা, সেটা হচ্ছে যত সিএস আছে সেগুলাকে আমাদের মেইন ক্লাস্টার যেটা আছে, আমরা মেইন ক্লাস্টার ছিল দুটা আর কি, ওই দুটার সাথে আমরা মার্জ করার ট্রাই করব, এবং সেখানেও মার্জ করা যায় কিনা সেটা দেখবো আর কি। যদি কন্ডিশন হচ্ছে ওই একই মাহালানবিস ডিসটেন্সের, এটা স্যাটিসফাই করলেই আমরা মার্জ করতে পারবো, নতুবা তাদেরকে আলাদা ক্লাস্টার আকারেই রাখতে হবে। এটাই হচ্ছে আলটিমেটলি ফাইনালি আনসার আসছে। ওকে, ঠিক আছে।
স্যার অ্যাসাইনমেন্টের ডেডলাইনটা কবে?
জাস্ট নেক্সট ক্লাসের আগ পর্যন্ত।
ওকে স্যার, থ্যাংক ইউ।
থ্যাংক ইউ স্যার।
ওকে,
আপনি
স্যার অ্যাটেন্ডেন্সটা
সবার অ্যাটেন্ডেন্স।
স্যার অ্যাসাইনমেন্ট সাবমিশন
হ্যাঁ, আমি গুগল ক্লাসরুমে একটা হচ্ছে অ্যাসাইনমেন্টের পোস্ট দিয়ে দিব, ওখানে সাবমিট করতে হবে।
স্যার ডেডলাইন কতদিন থাকবে?
নেক্সট ক্লাস।
ওকে স্যার, ঠিক আছে, থ্যাংক ইউ।
ওকে, থ্যাংক ইউ ভেরি মাচ।